Welcome to CSC 201, Lesson 10.1, Trails, Paths, and Circuits. The subject of graph theory began in the year 1736 when the great mathematician Leonhard Euler published a paper giving the solution to the following puzzle. The town of Königsberg in Prussia, now Kaliningrad in Russia, was built at a point where two branches of the Pregel River came together. It consists of an island and some land along the riverbanks. These were connected by 7 bridges as shown below. So this is an actual picture or map of the city. And we have land masses, the banks of the river A and C, D and C. And then B is an island in the middle. So this is just a picture of the rivers and the bridges. So the question is this: is it possible for a person to take a walk around a town, starting and ending at the same location, and crossing each of the 7 bridges exactly once? So you might pause the video and try a couple times. See, can you take a walk? If you start in on landmass A, and let's see, we would cross this bridge, and then we could cross back, and then we could cross C, and we could cross over to D, and we go back to B and O to D, and I've already crossed every bridge, and I'm stuck over here with no way to get back to where I started. So you can try different starting points, see if you can do it. To solve the puzzle, Euler translated it into a graph theory problem. So he noticed that all points of a given landmass can be identified with each other. So it doesn't matter whether you start over here or you start over here, you're on landmass A. And you can get anywhere on landmass A without crossing a bridge. So that was like a big simplification of the problem, to be able to think of landmass A as one point, each landmass as just a single point called a vertex. And thus, for the purpose of solving the puzzle, the map of Königsberg can be drawn like this, where each landmass is just a single point, and then which we call a vertex, and then we connect landmasses that have a bridge with an edge. These lines are called edges. So A has an edge to C because there's a bridge from landmass A to landmass C. So we can now translate the Königsberg problem about taking a walk to a question about tracing this graph. Can you start and end in the same place? So let's just choose C arbitrarily here. Can you trace the entire graph without picking up your pencil and without retracing an edge and finish at C? So let's just do a couple quick tries and see if we can do it. So we can go to A and then to B. If we go back to A, we're trapped. Like, we can't get out because we've already traced both edges that go into A. If I go to C, I can go to C, right? And now my only option is to go down to D, and I can go up to B. And now I have 2 options. I could go to A or to D, but then I'm trapped. Stuck, can't trace the last bridge. All right, so let's try one more quick try. Maybe we'll start somewhere else. We could start at D. So we have an option. We could go to C. Then we have a couple of options. Maybe we'll go to A. And then I could go down to B. And then I have some options. I could go to D. That wouldn't trap me. I don't want to go back up to A. That would trap me. I can't go to C. That would trap me. So let's go down to D. And then I can come back up to B. That's my only option. And now I have 2 options, but either way, I'm trapped without having traveled the last bridge. So 2 tries, I haven't been able to do it. We'll study graph theory a little bit more, and maybe we'll be able to answer this question definitively. Okay, so we have a lot of vocabulary at the start of this chapter. If G is a graph and V and W are vertices in G, a walk from V to W is a finite alternating sequence of adjacent vertices and edges of G. So a walk would look like a vertex and edge, a vertex and edge, and these things have to be adjacent, right next to each other. So a vertex traveled by an adjacent edge to an adjacent vertex, go another adjacent edge, like that. So that's a walk. And then a trail from V to W is a walk that does not contain a repeated edge. And a path is a trail, so it's a special kind of trail, so we can't repeat an edge, but it also doesn't repeat any vertices. A closed walk is a walk that starts and ends at the same vertex. A circuit is a closed walk that has at least one edge and does not contain a repeated edge. And a simple circuit is a circuit that does not have any other repeated vertex except the first and the last. So this little table may or may not be helpful to you. It's just a summary of those definitions. So I think what's most helpful is to just look at some walks and try to apply the definitions and see if we can classify these. So let's look at this first one, A. So it says start at vertex 1, right here, and then travel edge E1, and you land at vertex 2. Then travel edge E3 to land at vertex 3. Then travel edge E4 and land back at vertex 3. Then travel edge E5 and land at vertex 4. So I've traced my walk, and I want to try to classify it as a trail, a path, a circuit, or a simple circuit. So a trail, let's go back up and look. A trail is a walk that does not contain a repeated edge. So let's see, I went here, 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 here. No repeated edges. So it's a trail. And then remember, a path is a special kind of trail, right? So a path is a kind of trail that does not contain a repeated vertex. But we did repeat a vertex. We repeated V3. It showed up here and here. So it is not a path, just a trail. Okay, let's take a look at the next one. Here you'll notice that they only listed the edges and not the vertices. Sometimes they'll do that if it's very clear what the vertices are, and it's completely unambiguous what the walk is. So let's see if that's the case. So they say follow edge E1. So there's E1. Then E3, right there. Then E5, then E5 again. So I'm just going to kind of E5, E5 again, and then E6. So like that. Okay, so we repeated an edge, E5. So that's going to help me decide on what this is. So they say a trail that does not contain a repeated edge. So it's not a trail. That means it's not a path, because a path is a special kind of trail. So it's not a closed walk because we didn't start and end in the same place. And a circuit and a simple circuit are both closed walks. So this is none of these. None of these. It's just a walk. Okay, C, they just give me a list of vertices, which again is fine as long as there's no ambiguity about the walk we're taking. So let's just go ahead and trace the path by connecting vertices. So they say start at V2, and then go to V3, then V4, then V5, then V6, then V3, then V6, then V2. So we started and ended at the same place. So it could be some kind of, it's definitely a closed walk. It starts and ends at the same place. Is it a circuit? Did we repeat an edge? So let's just go through it again and see if we repeat any edges when we're tracing this. So it was V2, V3, V4, V5, V3 again. So we repeated a vertex, but not an edge. Then V6, then back to V2. So we repeated a vertex, but not an edge. So it's a closed walk because we started and end in the same place. At least one edge does not contain a repeated edge. So it's a circuit. Is it a simple circuit? Does not have any other repeated vertex except the first and the last. But we repeated a vertex. We repeated V3. So this is a circuit, but not a simple circuit. All right, take a look at part D. They say start at V2, then we go to V3, V4, V5, V6, and back to V2. So that starts and ends in the same place. It did not repeat any vertices or any edges, so that is a simple circuit. All right, so for part E, it says start at vertex 1, follow edge 1 to V2. Then it says follow edge 1 back to V1. So I just want to make it really clear that I'm following the same edge. So I go like that. So I repeated an edge 1, edge 1. So this is a closed walk because I started at V1 and ended at V1. But it is not a circuit because I repeated an edge, which means it's not a simple circuit either. So this is just a closed walk. For F, I just have a single vertex, V1. This is called a trivial walk, where you start and end at the same vertex. So the first vertex of this walk is the same as the last vertex. So it is a closed walk. But it does not contain an edge, which means it's not a circuit. It's just a closed walk from V1 to V1. It is also considered a trail from V1 to V1 because it does not contain a repeated edge. That's trivial because it doesn't have any edges, but it's also considered a trail. Okay, we're going to talk about connectedness. If G is a graph, two vertices V and W of G are connected if and only if there is a walk from V to W. An entire graph G is connected if and only if any two vertices V and W in G, there is a walk from V to W. So I'm just going to try to identify connected and unconnected. And visually, it can be pretty easy, usually, but not always. So this first one, A, it's connected. You can get from any vertex to another by tracing the graph. So we can start at V1 and say, I want to get to V5. I can follow a walk that gets me there. So this is connected. You can get from any vertex to another by following a walk through the graph. Now for B, it looks unconnected. So this is unconnected. You can't get from V4 to anywhere by taking a walk because there's no edge connecting V4 to any other vertex. Or for example, you can't get from V1 to V6. There's no walk you can take that will take you there. So this is not connected. Now this last one is one that is tricky because it looks connected. It looks like the entire thing is connected. However, you need to notice that these intersections are not vertices. They're not labeled with these black points. So those aren't vertices, which means there is no walk from, say, V3 to V4. If I want to get from V3 to V4, I have to follow edges, a series of adjacent edges and vertices. So I can't go directly to V4. There's no edge. I could go to V5, but then there's no edge to V4. This is not a vertex. Okay, so I can't stop there. So this is not connected. All right, so back to the Königsberg problem. We have learned a little bit of graph theory now. Is it possible for a person to take a walk around town, starting and ending at the same location and crossing each of the 7 bridges exactly once? You might maybe pause the video and try a couple more times, see what you come up with. The following definition generalizes the Königsberg bridge problem. So it creates a definition of a new kind of circuit. So far we only have a circuit or a simple circuit. Now, an Euler circuit for a graph G is a circuit, so we already know what a circuit is. It's a closed walk that does not repeat any edges. So an Euler circuit is a circuit that contains every vertex and every edge of G. So you have to be able to do the whole graph, go through the whole graph, starting and ending in the same place without repeating an edge. And it's a sequence of adjacent vertices and edges, that's a walk, that has at least one edge, starts and ends at the same vertex, uses every vertex at least once. So that was not part of our original definition of a circuit. It has to use every vertex of G at least once and every edge of G exactly once. So the theorems below generalize why the Königsberg walk is impossible. So this first theorem says if a graph has an Euler circuit, then every vertex of the graph has positive even degree. So quickly going back to the Königsberg bridge problem. So we have A, B, and C, and this was C. A, B, D. Two bridges, bridge, bridge, bridge. Okay. Now, part of why we couldn't do this when we tried is that we kept getting trapped. Like if we try to start at A, we could trace to B, and then we could go back to A. So you can leave A, you can come back to A, and you can leave A again, but we're never going back to A after that because there's no fourth bridge, there's no fourth edge. So the fact that there are 3 edges coming out of A means that you can leave, you can come back, and you can leave again, but you could never come back again. So the A cannot be a place where we start or finish. And then C is the same, like you can leave, you can come back, you can leave again, but you're never getting back to C without recrossing a bridge because there were only 3 bridges that go to C. So you could, if you started at C, you could leave, you can come back, you can leave again, but you can never come back. So you can't finish there either. And then D has 3 bridges, so it has the same problem. And then B, it has 1, 2, 3, 4, 5 bridges or 5 edges. And the number of edges going into a vertex is called its degree. So the fact that B has 5 means you can leave, you can come back, you can leave, you can come back, but then you can only leave. Okay, so the fact that there are 5 means you get trapped away from B. You can't finish at B either because you can leave, you can come back. You can leave, you can come back. You can leave, but you're never going to finish at B because there's no 6th bridge to bring you back. So it's the fact that these degrees are odd. They're an odd number of bridges at each landmass that tells you can't have this walk. You can't do this walk. So if a graph has an Euler circuit, then every vertex of the graph has to have a positive even degree, an even number of edges coming into that vertex. And then very related theorem, if a graph G is connected and the degree of every vertex G is positive and even, then G has an Euler circuit. So this graph does not have an Euler circuit because the vertices are all odd. In order to have an Euler circuit, all the vertices need to be even. So let's look at this one. So I want to just look at each vertex and I'm going to label it with its degree. So looking at vertex 1, we have 1, 2, 3 edges coming in. So the degree of vertex 1 is 3, and I automatically rule this out. There is no Euler circuit, right? In order to have an Euler circuit, every single vertex has to be even degree. Okay, so number 17, does this graph have an Euler circuit? So I'm going to label each vertex with its degree. So A has 2 edges coming into it, so it's got degree 2. B has 2. C has 2, D has 1, 2, 3, 4, that's even. E has 1, 2, 3, 4, also even. F has 2, G has 2, H has 1, 2, 3, 4, J has 2, and I has 2. Every single vertex has an even degree, so yes, there is an Euler circuit, and we want to find one. Your book gives an algorithm on how to find one, but once you know there is one, it's usually pretty easy to find just by trial and error. So I might start at A and go to B, 1, that's my first edge, and then I'd go 2 and 3, and then just using a little common sense here, I'm not going to go back to A because then I'm trapped, so I'm going to take one of my other two choices. I think I'll go here from D to I, and then I only have one choice here and here. Now at vertex H, I have 3 choices. I think I'll go 7, 8. I'm not going to go back to D at this point because then I'm trapped. So I think I'll go 9, 10, 11. And then I can go back to D. And then I can go back to A. So there's many possible Euler circuits. You may have found a different one. Totally fine. All right, so sometimes it's possible to almost have an Euler circuit. So that is, we could find a way to visit every vertex at least once and traverse each edge exactly once if we're allowed to start and end in different locations. And this is called an Euler trail instead of an Euler circuit. So an Euler trail, again, traces each edge exactly once, visits every vertex at least once, but it does not have to start and end at the same place. This is possible if we allow V and W to have odd degree. The starting and ending points can have odd degree, but that's it. For example, we have a floor plan shown below for a house that's open for public viewing. Is it possible to find a trail that starts in room A, ends in room B, so starting and ending in different places, passes through every interior doorway of the house exactly once? If so, find such a trail. So hint, first convert the floor plan to a graph where each room is a vertex, right? So each room we're going to condense down to a single point, kind of like we did with the land masses in Königsberg. And then edges are going to represent doorways from one room to another. So let's see, my vertices, I've got A, room B, room C, and then G, H, and I, and then I've got F, E, K, J, and D. So those are all the rooms. I'll go back and label them. A, B, and C. G, H, I, F, and E, and then K I put in the corner, J, and D. Now, you can put these points, these vertices, in any arrangement you want. I kind of tried to mirror the floor plan, but they could be in any arrangement that you want. The only thing that matters is whether or not there's an edge connecting two rooms. So A, what does A connect to? So if we look at the floor plan, the only room that A is connected to via a doorway is G. So I'm going to draw an edge from A to G. And then B is only connected to C. So I'll draw that edge there. And then C is connected to B and to D. I already have the edge to B, so I'll add the one to D. D is connected to C and to J. I think I'll just go in alphabetical order here. So E is connected to F, H, I, and K. E has 4 doorways. 1 to F, 1 to H, 1 to I, and 1 to K. All right, so that was E. F has a doorway both to E and to H. So we'll add the connection from F to H. G has doorways to A and to H. H has 3 doorways, G, F, and E, which I already have drawn in. I has 2 doorways, 1 to H and 1 to E. So I already drew the 1 to E. I'm going to add the 1 to H. I has 2 doorways to H and to E, already drawn. K has 2 doorways, 1 to E and 1 to J. And then, I lost alphabetical order there. Now I'm going to go to J. J has 2 doorways, 1 to K and 1 to D, and those are already drawn. All right, so that's my entire graph translated from a floor plan. Now I want to look at the degree of each vertex. So A has degree 1. There's only one edge coming into A. G has 2, H has 4, I has 2, 2, 2, 2, 2. B has 1, F has 2, and E has 4. So every single vertex is even except for the starting points A and B. So yes. All vertices have even degree except A and B, where we're trying to start and finish. So yes, this has an Euler trail. Another special kind of circuit of a graph is called a Hamiltonian circuit. Given a graph G, a Hamiltonian circuit for G is a simple circuit that means it starts and finishes in the same place and does not repeat any vertices except the first and the last. Okay. It says nothing about edges. We do not have to care about edges at all. We just have to make sure we visit every vertex exactly once, except the first and the last, which gets visited twice because it's the same. Okay, so the difference between a Hamiltonian circuit and an Euler circuit is subtle. In an Euler circuit, you can visit vertices more than once, and you must travel every edge exactly once. In a Hamiltonian circuit, you must visit every vertex exactly once, and you don't care about the edges at all. So, for example, we have a graph drawn here. Imagine that every vertex represents a city somewhere in the world, and you want to find a circuit that visits every city exactly once. You don't care about the edges at all. Like, you don't care if you've traveled from Paris to London and London to Paris. In fact, you don't have to go from London to Paris or vice versa at all. You could go, they don't need to be connected on your trip around the world. Okay, so they don't have to happen in sequence, even if they're connected by an edge. So you would want to find a circuit that visits every city exactly once. You need not traverse every edge to do it. So, for example, if you follow the black edges here, we can visit every city once, but you'll notice we don't cover every edge. So if we start at A, we could go B, C, D, E. Then I'm not going to go back to A. I've already visited A, so that edge never gets covered. I'm going to go to F, then to G. Then I have a choice here, but I'm going to go to H, I, J, K, L. I've already been to H, so I'm not going to go there. I'm going to go out to M. I've already been to F, so I'm not going to go there. N, O, P, Q, R, S, T. And you visit every city, but there are several edges that never got covered. All right, so finally, we discuss how we determine if a graph has a Hamiltonian circuit. So a graph G has a Hamiltonian circuit. That means that G has a subgraph H. A subgraph is just a subset of the components of H. So you can take away some vertices and some edges from G, and you're left with a subgraph of G. So if a graph G has a Hamiltonian circuit, then it has a subgraph H with the following properties. So H has to contain every vertex of G. You can't take any vertices away. H is connected. H has the same number of edges as vertices, and every vertex of H has degree 2. So let's see if we can apply this proposition. Does the graph below have a Hamiltonian circuit? So I want to try to draw a subgraph that has these properties. Try to draw a subgraph H with the 4 properties from the proposition. Okay, so H has to contain every vertex of G. So I have to have all the original vertices, A, E, B, C, and D. So I've got all the vertices. I'll label them. Okay, now H has to be connected, which means I can't leave one of these vertices floating. And H has the same number of edges as vertices. So I've put 5 vertices down. I have to draw 5 edges. My original graph has 1, 2, 3, 4, 5, 6 edges, which means I must remove an edge, right? And which is okay because this is a subgraph. Okay, so a subgraph means you could remove edges or vertices, and that's a subgraph. So I have to remove one edge, and by doing so, my graph has to remain connected, and every vertex of H has to have degree 2. So let's see, if I remove this edge, then these 2 vertices are only going to have degree 1. Same with over here. I can't remove this edge because these 2 vertices would both have degree 1, and they have to have degree 2. So I can't remove this one or this one. So it means I have to remove one of these 4 that kind of crisscross. If I remove this one, then C has degree 1 and B has degree 3. That won't work. If I remove this one, A has degree 1 and B has degree 3. Can't do that. If I remove this one, E has degree 1 and B has degree 3. And if I remove this one, then D has degree 1 and B has degree 3. So there's no way that I can draw 5 edges connecting these 5 vertices and satisfy every vertex has degree 2. So this is impossible. This will fail property 4 no matter which edge we remove to satisfy property 3, right? So to satisfy property 3, we have to remove an edge. And no matter which edge we remove, we cannot satisfy property 4, so this does not have a Hamiltonian circuit.